In this video, we'll be giving a running time analysis of the merge sort algorithm. In particular, we'll be substantiating the claim that the recursive divide and conquer merge sort algorithm is better, has better performance than simpler sorting algorithms that you might know, like insertion sort, selection sort, and bubble sort. So in particular, the goal of this lecture will be to mathematically argue the following claim from an earlier video, that in order to sort an array of n numbers, the merge sort algorithm needs no more than a constant times n log n operations. That's the maximum number of lines of code it will ever execute. Specifically 6 times n log n plus 6n operations. So how are we going to prove this claim? We're going to use what is called a recursion tree method. The idea of the recursion tree method is to write out all of the work done by the recursive merge sort algorithm in a tree structure, with the children of a given node corresponding to the recursive calls made by that node. The point of this tree structure is it will facilitate an interesting way to count up the overall work done by the algorithm and will greatly facilitate the analysis. So specifically, what is this tree? So at level 0, we have a root. And this corresponds to the outer call of merge sort. Okay, so I'm going to call this level 0. Now this tree is going to be binary in recognition of the fact that each invocation of merge sort makes 2 recursive calls. So the 2 children will correspond to the 2 recursive calls of merge sort. So at the root we operate on the entire input array. So let me draw a big array indicating that. And at level 1 we have one subproblem for the left half and another subproblem for the right half of the input array. And I'll call these first 2 recursive calls level 1. Now, of course, each of these 2 level 1 recursive calls will themselves make 2 recursive calls, each operating on then a quarter of the original input array. So those are the level 2 recursive calls, of which there are 4, and this process will continue until eventually the recursion bottoms out in base cases when there's only an array of size 0 or 1. So now I have a question for you, which I'll give you in the form of a quiz, which is at the bottom of this recursion tree corresponding to the base cases, what is the level number at the bottom? So at what level do the leaves in this tree reside? Okay, so hopefully you correctly guess that the answer is the second one. So namely that the number of levels of the recursion tree is essentially logarithmic in the size of the input array. The reason is basically that the input size is being decreased by a factor 2 with each level of the recursion. If you have an input size of n at the outer level, then each of the first set of recursive calls operates on an array of size n over 2. At level 2, each array has size n over 4, and so on. Where does the recursion bottom out? Well, down at the base cases where there's no more recursion, which is where the input array has size 1 or less. So in other words, the number of levels of recursion is exactly the number of times you need to divide n by 2 until you get down to a number that's at most 1. And recall that's exactly the definition of the logarithm base 2 of n. So since the first level is level 0 and the last level is level log base 2 of n, the total number of levels is actually log base 2 of n plus 1. And when I write down this expression, I'm here assuming that n is a power of 2, which is not a big deal. I mean, the analysis is easily extended to the case where n is not a power of 2. But this way, we don't have to think about fractions. Log base 2 of n then is an integer. Okay, so let's return to the recursion tree. Let me just redraw it really quick. So again, down here at the bottom of the tree, we have the leaves, i.e. the base cases where there's no more recursion, which when n is a power of 2 correspond exactly to single element arrays. So that's the recursion tree corresponding to an invocation of merge sort, and the motivation for writing down, for organizing the work performed by merge sort in this way is it allows us to count up the work level by level, and we'll see that that's a particularly convenient way to account for all of the different lines of code that get executed. Now, to see that in more detail, I need to ask you to identify a particular pattern. So first of all, the first question is, at a given level j of this recursion, exactly how many distinct subproblems are there as a function of the level j? That's the first question. The second question is, for each of those distinct subproblems at level j, what is the input size? So what is the size of the array which is passed to a subproblem residing at level j of this recursion tree? So the correct answer is the third one. So first of all, at a given level j, there's precisely 2 to the j distinct subproblems. There's one outermost subproblem at level 0. It has 2 recursive calls. Those are the 2 subproblems at level 1, and so on. In general, since merge sort calls itself twice, the number of subproblems is doubling each level, so that gives us the expression 2 to the j for the number of subproblems at level j. On the other hand, by a similar argument, the input size is halving each time. With each recursive call, you pass it half of the input that you were given. So at each level of the recursion tree, we're seeing half of the input size of the previous level. So after j levels, since we started with an input size of n, after j levels, each subproblem will be operating on an array of length n over 2 to the j. Okay, so now let's put this pattern to use and actually count up all of the lines of code that merge sort executes. And as I said before, the key idea is to count up the work level by level. Now, to be clear, when I talk about the amount of work done at level j, what I'm talking about is the work done by those 2 to the j invocations of merge sort, not counting their respective recursive calls, not counting work which is going to get done in the recursion lower in the tree. Now, recall, merge sort is a very simple algorithm. It just has 3 lines of code. First, there's a recursive call, so we're not counting that. Second, there's another recursive call. Again, we're not counting that at level j. And then third, we just invoke the merge subroutine. So really, outside the recursive calls, all that merge sort does is a single invocation of merge. Further, recall we already have a good understanding of the number of lines of code that merge needs. On an input of size m, it's going to use at most 6m lines of code. That's an analysis that we did in the previous video. So let's fix a level j. We know how many subproblems there are, 2 to the j. We know the size of each subproblem, n over 2 to the j, and we know how much work merge needs on such an input. We just multiply by 6, and then we just multiply it out, and we get the amount of work done at a level j, okay, at all of the level j subproblems. So here it is in more detail. All right, so we start with just the number of different subproblems at level j, and we just noticed that that was at most 2 to the j. We also observed that each level j subproblem is passed an array as input, which has length n over 2 to the j. And we know that the merge subroutine, when given an input, given an array of size n over 2 to the j, will execute at most 6 times that many number of lines of code. So to compute the total amount of work done at level j, we just multiply the number of problems times the work done per subproblem, and then something sort of remarkable happens. We get this cancellation of the 2 to the j's, and we get an upper bound, 6n, which is independent of the level j. So we do at most 6n operations at the root, we do at most 6n operations at level 1, at level 2, and so on. Okay, it's independent of the level. Morally, the reason this is happening is because of a perfect equilibrium between 2 competing forces. First of all, the number of subproblems is doubling with each level of the recursion tree, but secondly, the amount of work that we do per subproblem is halving with each level of the recursion tree. Since those 2 cancel out, we get an upper bound 6n, which is independent of the level j. Now, here's why that's so cool, right? We don't really care about the amount of work just at a given level. We care about the amount of work that merge sort does ever at any level. But if we have a bound on the amount of work at a level which is independent of the level, then our overall bound is really easy. What do? We just take the number of levels, and we know what that is. It's exactly log base 2 of n plus 1. Remember, the levels are 0 through log base 2 of n inclusive. And then we have an upper bound 6n for each of those log n plus 1 levels. So if we expand out this quantity, we get exactly the upper bound that was claimed earlier, namely that the number of operations merge sort executes is at most 6n times log base 2 of n plus 6n. So that, my friends, is a running time analysis of the merge sort algorithm. That's why its running time is bounded by a constant times n log n, which, especially as n grows large, is far superior to the more simple iterative algorithms like insertion or selection sort.